but
It's being recorded.
so it's already started. So
E
can pop here. Okay, well, good morning, everyone. Welcome to EECS 151 251A, Introduction to Digital Design and Integrated Circuit. In today's lecture, we're going to quickly wrap up our discussion on FSM, in particular, how we actually implement FSMs in Verilog. Some of you who have already started Lab 3, you probably have already seen some aspect of that in both ASIC and FPGA lab. And we'll also, Ben will get us started on the RISC-V side, a brief overview of the RISC-V history and some of the key components when we think about building the data path. So now we get into, I guess, we try to get yourself ready, our students ready for the final project mode to see all the different components and how you can actually start thinking about the project or the data path you want to design for your project. So for today, I guess before we get to the content, I was thinking what would be a good way to, I guess, loop into the RISC-V discussion. I guess a couple of things. Well, I prepared this yesterday, which is pretty cool. This is announced earlier this year on some of the NVIDIA support in really thinking about how they can broaden their CPU platform, right? So over earlier this year, like we talked about, I think some folks mentioned Grace Hopper, right? NVIDIA has been having their own ARM-based CPUs and together with GPU to set up their DGX system, right? So Grace Hopper is a good representation. And for a lot of data center design, you can actually use NVIDIA GPU and also pair with different x86 chips. We'll talk a little bit more updates on that front, and typically from either Intel or AMD. Earlier this year, what NVIDIA announced at RISC-V Summit is actually they are also opening up the ecosystem to RISC-V. What does that mean? It basically, if you are a RISC-V CPU vendor, you can actually drive the CUDA. You have the CUDA driver support on the RISC-V platform so that the RISC-V CPUs can also be paired with NVIDIA GPU. So now the ecosystem is a lot broader, right? So when you actually want to get the GPU working, it's a lot of applications want to run on GPU, but it's not only the GPU, right? The CPU is a very important component. It started with x86-based platform from Intel or AMD, then gradually NVIDIA has been doing their own ARM-based CPUs, and we talk about NVIDIA's intention to even acquire ARM earlier, I guess, the last couple of years. And now, actually, NVIDIA is further opening up the platform so that even RISC-V-based CPU can also be partnered with NVIDIA GPU, right? So this is pretty exciting that there will be more vendors can actually leverage NVIDIA's GPU-based platform, but pair with their own CPU, less dependent on either the ARM-based ecosystem or x86-based ecosystem to actually set up different GPU, either desktops or even servers. So this is already pretty exciting. I was thinking about this is a good way to actually get into RISC-V, but and related to some of the NVIDIA's effort. There is something new just happened this morning. Another stock actually popped 20+% this morning. Which one?
NVIDIA paid $5 billion to buy some part of the stock from Intel and announced that they will publish a07 based on Intel's x86 and NVIDIA's chip.
Yeah, so there are more collaboration going on between two very interesting companies, Intel and NVIDIA. Which stock goes up 20%?
It's not ours.
It's not. If it's NVIDIA, I guess Ben can retire at this point. So Intel stock went down. I guess NVIDIA went up like 2 or 3%. It's like still positive, right? So this is a good news for Intel. And this is pretty interesting. I was not expecting that, but it kind of makes sense as well. If you think about NVIDIA platform, we talk about there's a lot of fairly complex, dependent, and very intertwined relationship between semiconductor companies, right? We talk about, okay, all the semiconductor companies, everyone has their own CPU portfolio. AMD has both CPU and a GPU portfolio. There's definitely like some flavor of competition going on, right? But if you look at the ecosystem, when you actually try to sell as many GPU as possible, you also want to have different vendors and can provide the CPU part, right? We talk about this is like opening up to more CPU vendors that using RISC-V based system. The Intel collaboration is also very interesting as we look at the data center, Intel and AMD CPU, right? We see AMD CPU is actually catching up and being more adapted in some of the hyperscaler designs. If you were NVIDIA, right, if you are Jensen, right, you want to have this ecosystem more competitive, right? You want to avoid monopoly, even for x86. You want to have a healthy ecosystem that both Intel and the AMD CPUs can actually work closely with GPUs to have this kind of more healthy ecosystem. So this is pretty interesting. We'll see how the, I guess, collaboration evolves over years. I think the first announcement sounds like both investing in Intel and also get started on some of the both gaming, desktop, and also data center CPU and GPU design part. There's also the chiplet-based design through Intel packaging, and Intel has actually very strong packaging component. We'll see whether this will actually also go to fabrication, right? We talk about Intel also have their fabrication. I haven't seen a lot of announcement related to actually using Intel fab, but I wouldn't be surprised. This is also part of the discussion, giving things we want to do more domestically and also less reliant on TSMC, right? So a lot of interesting components going on in the ecosystem, and sometimes you're partners, sometimes you're competitors, right? It's like very complicated relationship, but that's why this field is so exciting, right? You want to build bigger thing, you want to collaborate with others, but you also want to avoid monopoly so that you can actually work with different vendors. So RISC-V is collaborating with CUDA-based NVIDIA ecosystem, but there is still a healthy mix of both RISC-V, ARM, and x86 that can, and even actually IBM PowerPC, right, can actually get connected with GPU platform. So with that, let's get started on today's topic. We started the finite state machine discussion. We talk about what they are. In particular, we mentioned there are two flavors finite state machine, right? Moore machine and mealy machine. For both flavor, we mentioned there are like three components in finite state machine, right? First, you need state element, right? To remember where you are, what has happened, right? Then you have two flavor of combinational logic. The first one to actually tell you how to advance to the next state, right? From current state, how do you want to advance to the next state? The second part is actually how do you want to actually produce your output, right? The difference between Moore and the mealy is like for the output part, for Moore machine, output is only dependent on the current state versus mealy machine depend on both the current state and also the input, right? So the second combinational logic that are different. For today's discussion, we'll briefly mention how we actually realize this in Verilog, right? We mentioned like a lot of the earlier steps can be very similar in actually doing this by hand and also versus implementing this in Verilog. You want to specify the function, you want to draw the state transition diagram. We mentioned the circles indicating the states and the edges indicating the state transition, how it changed and based on different input, right? And then you want to assign different encodings to the symbolic table. After that, you'll basically want to code in Verilog, right? So here we'll talk about some of the high-level principles, how we realize that, and we'll see a couple of examples. First, we always want to actually have a good representation, use parameters to use encoded states so that it's easier to remember just like what are the states instead of using all the different bits directly. You also want to have separate always block. We mentioned that you can use always block for state transition. For sequential logic, you can also use always block for combinational logic, right? In particular, here we mentioned they're both state transition and that's combinational logic in a finite state machine. In particular, one thing really nice with always block to describe combinational logic is that you can use case statement, right? We mentioned you have the different transitions and this can be expressed using case statement. So this is pretty handy. You will use always block to do that. And in particular, we talk about Moore and the mealy machine, and the key difference is how the output is computed, right? Whether it's only dependent on the current state or it's dependent on both on the current state and also the input. So here's a lot of high-level principles. Let's take a look at some examples, right? So when we think about finite state machines, we mentioned we have the state transition diagram. Each node represents a state, and edges represent how state actually transitioned between different stages. And that typically dependent on input. A difference between Moore and the mealy is here for Moore machine, output is only dependent on the current state versus mealy machine, you will see something like more like input and output, where output is a factor of both current state and input. And when you get to actually circuit realization, right, as we discussed, there is always a state register to actually store what are the current states. And then the two type of combinational logic. One is to determine what the output is. The second is to determine what the next state should be, right? So those are the key principles in thinking about a finite state machine. So let's take a look at an example. So here, this is I guess this is a state transition diagram we saw earlier. We have three states. We transition from idle to S0 and S1. Those are two states we have. And here, we are doing a Moore machine as the output only dependent on the current state, right? So now what we want to do is to actually implement this state transition diagram into a Verilog, right? So at this point, you folks should be fairly fluent with Verilog through your lab exercises, and you will do a lot more throughout the semester. It's a fun language. It's a fun language. You will enjoy speaking Verilog for the rest of the semester. So what do we do, right? We instantiate a module. This module is our FSM. We have all the input. We have input, clock, and reset. We have reset, always have reset in your design, right? What's the default state when the circuit wakes up? We talk about state encoding, right? Here we like to have parameters to actually constant to actually indicate what the states are, right? So that is a lot easier to actually just write directly the state instead of using all the bits in your design. And we like to actually, we mentioned there are registers needed to store the current state, right? Where like the state element need to be stored in register to indeed hold the state of the FSM. We also notice there are a couple other components also used declared as reg in Verilog. Those are not intended to mean actually register because we only have register to store the current state. Those are declared as reg because you want to use them in always block. They need to be reg so that we can actually assign it. Joy?
What is the purpose? Like this is not like a macro like define something.
Right, this is basically define the state encoding. You basically define the constant, right? What are the like idle and you can think about you declare I guess a constant using like using a word instead of using the bits directly, and this is a lot more handy to do that this way.
This instead of just doing like the macro.
How would you do macro in?
Don't you like there are ways to like have constants like when you. For example, like in the test bench, you would have like the apostrophe and then second. And then
there are certain things you can do in test bench, but you cannot do that in the design. So test bench is only for simulation time. It's like the simulation component. Here is actually in the design. Your intention is here is a design constant that I like to declare. So everything here is in your design under test, not in the test bench. Right, so here we're doing the design part. There are certain like new syntax that is more flexible syntax that you can use in test benches, but here we're doing the design part.
So there are no ways to define a constant other than parameter in the device under test.
I think there are the.
Are you asking about why not use a tick define?
Yeah.
So you could, tick defines are global to your all of your Verilog code. Whereas the parameter, as it notes on the slide, are constrained to the local module, so it's much safer to use it just with the local module. So.
Unless you actually want to actually have a global variable that's actually used for the design.
There is still this define idea in the device under test.
Yes, it's a preprocessor macro. They're both preprocessor macros. It's just this one is constrained to the module, so it's safer.
Right. Yeah, and it's better to have more locally defined constant instead of having global constants, and you lose track of where things are. Good question. So here are the different declaration, and we talk about the always block, right? So here we want to assign state to what our current state should be, right? We come out of reset, we are in the idle state. Otherwise, every time we actually assign the next state to the current state, right? And how we actually calculate the next state will be the separate design. That's like the combinational logic we mentioned earlier, but here is a state transition. So we talk about three parts. We already talked about state transition. Now we like to actually declare the combinational logic part, right? Using like the case statement we mentioned earlier. depends on the current state, we can actually assign both the output and also the next state, right? So here, because we're doing a Moore machine, the output is only depends on the current state. If it's idle, we actually have a output is 0. If it's S0, I guess output is also 0. If S1, output is 1, right? For next state, that depends on the input, right? If input, so you are in the idle state, if input is 1, that's this edge, we actually next state we get to S0, right? So that's how we actually specify the relationship from depending on the current state, how we go to the next state, and how we actually assign output. Does this part make sense? So far, so good? Okay, so we mentioned both Moore machine and Mealy machine, right? So for the state transition, it's always the same. You always assign the next state to the current state. But for Moore machine and the Mealy machine, the key difference is where output is, right? Whether output is actually dependent on input or the output is only associated with a state. Right here, for the Moore machine we mentioned earlier, output is only associated with state. You just declare, assign output directly. For Mealy machine, you actually want to define, depend on the input, your output might be different. If input is 1, output is 1. If input is 0 for this state, output stay at 0, right? So this is basically very clearly how we can actually express a different intention in Verilog for the two style machines. Question? You want to do a if you have a 2D array, oh, you can actually use the generate statement we mentioned earlier. Right. So that's always pretty handy if you actually need to assign a lot of, yeah. Any other questions? Okay, again, this is very high level. You folks will actually play with more different design points in your lab, and that's like where you actually get to practice the different way of thinking about the design. Okay, with that, just a quick recap. We talk about, for finite state machine, we talk about sequential logic. In particular, we have a memory element, and a very representative way of realizing sequential machine is using finite state machine. Again, 3 components. We need to store the current state, and we need combinational logic to calculate what the next state is and what's the output. And one thing you will see a lot is like 2 different flavors of designing finite state machine, and it's always depends on whether your output is only associated with current state or it's associated with both current state and inputs. Okay, so that's the highlights of the finite state machine, and that wrap up our combinational and sequential logic discussion and how that can be realized in Verilog. For announcement, well, so first homework, we have homework to do, I guess this week, and homework 3 will start, and that will be more focusing on the finite state machine, and you will get to play with different finite state machine component. For enrollment, at this point, I think everyone who intended to take the class should be enrolled already, minimally in one of the labs. All of the folks who are still stayed on the wait list until Tuesday who wanted to take the class should be enrolled at this time. The ASIC wait list is significantly longer than we can absorb. So some of the students want to take both. We cannot accommodate that. If some students who are already in the IPG lab but also want to do ASIC lab, it's very hard to absorb that. But if you want to get enrolled in the class, in the lecture, and you want to take one of the lab, it should already happen at this point. If not, let us know, but we're very excited about the semester, and I think we have finalized the enrollment, and everyone should focus on the class at this point. Any questions about logistics side? Okay, great. With that, we'll transition to Ben's part on the RISC-V design.
Okay, we'll take a 1-minute break while I get the microphone attached. Okay, how am I sounding? Can someone in the back 3 rows give me a thumbs up that you can hear okay? Cool, great. Oh, good morning, everyone. It's a pleasure to be here. I am looking forward to talking about RISC-V with you all today to kick off our sort of second segment of course material. Before I do that, I'm going to have a very brief interlude on a totally unrelated topic. I just found out about this morning, but it seemed relevant potentially to some of you all. For those of you that are maybe plugged into the professional circuit design community, or if you're interested in learning more about it, the International Solid State Circuits Conference, or ISSCC, is the kind of world premier circuits research conference that takes place in San Francisco every year in February. It has lots of papers and short courses and presentations on both analog and digital design. So it's much more focused on chips and circuits than things higher up the stack. But if this is a life path that you are interested in pursuing, it's a good idea to familiarize yourself a little bit with the professional landscape and consider attending this conference. We're very privileged in that it's always local for us because it's in San Francisco every year. So you never have to worry about paying for flights and hotel rooms and things. You just have to pay for registration. But there's a special program this year, which is what I'm showing on the slide, which is this Next Gen Circuit Designer Workshop. So it's targeted at sort of, I'd say, probably 3rd or 4th year undergrads or early career grad students, although any undergrad is welcome to apply to attend. You do get your conference registration paid for if you gain acceptance to this workshop. So it means you get to attend ISSCC for free as well, which is a very cool opportunity. So if you are interested in learning more, there's a QR code there with the application, or you can just Google for this phrase and it should pop up the information page. But if this is a career or a research life direction that you think you might be interested in, I thought this would be a cool opportunity for some of you. So if you have more questions about it or want to chat more about ISSCC, feel free to find me after lecture. But let's move on to our topic today, which is RISC-V. Before we get into content, I want to do a quick check about a way that I want to regularly get feedback from you all during lecture. It's a very simple thing. It's called Fist to 5. Some of you may have heard of it. So occasionally I'm going to ask you a question and simply ask you to respond on a numerical scale from 0 to 5 by holding up 0 to 5 fingers. It's pretty straightforward. So just as a practice, can folks give me a fist of 5 on how awake you're feeling this morning? So a 5 would be, I'm totally awake. Maybe I had a bunch of coffee this morning. Wired. 0 would be I can't hear you. I'm literally asleep right now. Okay, so I'm seeing some 3s and 4s. I think is typical. A few 2s. Few people are really tired. I'm sorry to hear that. I'll do my best to keep you awake for the next 45 minutes. Okay, thanks. So we'll be using that occasionally as we go through the lectures, mainly just to check in about understanding about different topics or how things are going. Before we zoom into RISC-V itself, I do want to step back a bit because, again, this is a transition point into a new segment of the course. It's kind of a little bit of a different way of looking at things. So I want to just recap some of what we saw in the earlier lectures about kind of what I think of as the 4 big ideas in digital design. And really, these are really key ideas for any engineering discipline. But I would argue that for digital design, they're especially important. And so I'm going to get on my soapbox for a few minutes and just hammer that home. The first of these is hierarchy. We're all familiar with hierarchy in the context of Verilog. We have modules that instantiate other submodules. That's a very clean example of hierarchy. But it's just, in general, this idea that a thing can contain other smaller things that themselves can contain other smaller things.
right? Very, very useful concept for managing complexity. All of these concepts are ways to manage complexity, right? Which is just such a critical thing for a digital designer to understand. The next concept is modularity, also sometimes referred to as black boxing, which is why I've represented it with a black box in the cartoon. Modularity means presenting clean interfaces for a particular thing to the rest of the world, a well-defined way that a thing interacts with the rest of the world, such that the rest of the world doesn't need to know about the insides of that thing in order to make it work. In a software context, modularity often takes the form of an API, an application programming interface. So in hardware, we want to impose a similar concept where when you define, again, to use a Verilog example, when you define a Verilog module, the way that it behaves should be well defined to the outside world, through the list of inputs and outputs, and perhaps some hopefully explicit description or documentation of how it's supposed to behave, so that things interacting with that shouldn't need to understand the internals in order to make it work. The third is very straightforward, just regularity, also known as reuse. So if you have things that are the same, just stamp out copies. Don't design a new one. I've got a perfectly good right hand. I don't need to go design another hand. I'll just stamp out another one, and I have two hands, right? It's very straightforward. But related is that if you have two things that are mostly the same, it's probably worth making them exactly the same so you can make copies and then defining the difference somewhere else, right? Because regularity, again, is a really important way of managing complexity. And the last and most important one that I want to harp on, and it's so important, I'm going to have a whole other slide on it, is this idea of abstraction. And this is something that we've already talked about in detail, but I do want to revisit it and just make sure it's always tucked away in the back of your minds. Abstraction is pretending that something complicated is really simple. So pretending that Prof. Chow with all of her human complexities is just a circle with two dots and a line, right? There are times when that is really useful, when it's useful to pretend that. For example, if you're drawing cartoons or something, there are times when that's really not useful and you need to strip away the abstraction and actually think about what's underneath. And a lot of the innovation and cleverness and research in digital design is figuring out, building intuition for when to respect the abstraction, which is most of the time, because you need to manage complexity, and when to actually strip away the abstraction and think about what's going on below. So let's talk more about that. This is a slightly different view of abstraction compared to the slides that you saw earlier in lecture. This is less focused on how we design and more focused on what exactly we are designing. And so we'll talk about each of these layers in turn, right? So at the top of the hardware abstraction is this idea of architecture. We're going to talk about architecture today. We're going to talk about the RISC-V ISA, the instruction set architecture, right? And ISA is a contract between hardware and software. And so the software programmer's abstraction of hardware is just you put in an instruction and the hardware does the thing that the instruction says it's supposed to do, right? If I'm writing and of course there's even more abstraction on top of this in terms of, higher level programming languages and so forth. But from the hardware down, this is what software sees. And so if I'm writing a Python script to, automatically feed my cat or whatever you all write Python scripts for, I don't want to worry about how my processor is designed or pipelined or what its frequency is. I just want to put in instructions and get out the answer. So this is one abstraction, the sort of highest level of hardware abstraction. Below the architecture abstraction, we're going to start talking about this today and in future lectures, is this idea of microarchitecture. So these are things that are not necessarily visible to the software programmer, but they're important for how to implement the actual thing that you're saying to software you're going to do. An example of a microarchitecture design decision is this idea of pipelining, how many pipe stages to put in your RISC-V processor. We'll talk about that in a future lecture. But again, if you're designing microarchitecture and pipelining, you don't want to be thinking about, oh, well, how exactly might I code this in Verilog? What is the combinational logic going to be? What is the sequential logic going to be? This is at a higher level, perhaps a detailed block diagram of what you're building, or a simulator view. Okay, let's one step down further. Now we're in the realm of Verilog, register transfer logic. We will spend a lot of this course at this level of abstraction. I do want to make a distinction that Verilog is not itself synonymous with RTL. The register transfer abstraction is saying something very specific, which is that everything I want to do with digital logic can be represented with state elements that update once per cycle on a clock, and then combinational logic that kind of instantaneously figures itself out, no matter how much combinational logic you're doing, right? So every register transfer abstraction has two phases. It has update the registers, do the combinational logic, update the registers, do the combinational logic, right? And that's the level of abstraction we're at. We're not worrying about, oh, well, what are the standard cells that I actually would need to, implement, or what's the Boolean logic function to make that work, right? I can just write down, oh, A times B, and that's simple enough. That's good enough at this level of abstraction. Verilog is a very imperfect mechanism for representing the RTL abstraction. And there are a lot of ways that you can write Verilog where you're not actually at this level of abstraction. And you need to be careful to avoid that, or else you get weird, buggy behavior. But Verilog is one way that we represent the RTL abstraction in this class. Okay, let's step down one more. Let's peel back the curtain. So below RTL, we have this idea of standard cells, Boolean logic, Boolean optimization. We've talked about that in the last few lectures. So this is going beyond A times B and thinking about, well, what are the actual collection of logic gates, that perform simple Boolean functions that can implement A times B? How can I build A times B with ands and ors and inverters and nands? We're going to talk about that specific question later in the class. But we've talked about some general techniques for thinking about Boolean logic and Boolean simplification in previous lectures. But when we're manipulating logic gates or Boolean functions, we definitely don't want to be thinking about, well, wait, how do I make this out of transistors again? Do these circuits have delay? Are they consuming power? I don't want to think about all that stuff when I'm making my K-map, right? We abstract it away. And so this is, again, a really powerful way to live at this level of abstraction. Okay, now we're getting down to the low-level stuff. Each gate, if you peel back the curtain, is made of transistors. It's made of wires, right? We can represent these transistors with a schematic like you see in the cartoon here. These gates are not ideal instantaneously executing a Boolean function, right? There's actual voltages and currents and other ungainly stuff flowing around in there, right? We have to think about, well, wait, how long does it actually take for the electrons to move the voltage around? Voltage is no longer 0 or 1, right? It's a value. It's 1 volt or 0.2 volts or something like that. When we strip away this layer of magic abstraction at the digital, level, we have to start thinking about all this lower level stuff. And we're going to talk about that stuff later in the lecture. But we can go even deeper, right? In order to implement a transistor, which is just a drawing on a page, it's just a schematic, we need to actually have a layout, right? We need to actually lay down different rectangles in different layers of metal and polysilicon, things with all sorts of weird names. We won't learn that much about that in this class. It's a little bit outside of scope. There are other courses where you talk more about physical layout. In particular, in this class, we abstract physical layout in two ways. One is that it's encapsulated in this really nice concept called the standard cells that implement the Boolean gates. And someone has already done the standard cell layouts for you. And then to connect those standard cells, we have wires, which again, wind up as just rectangles, but the EDA tools are doing that for you. And so you can look at the layouts that are generated by Innovus in the ASIC lab if you like, but it's not a core concept in this class, but it's always there, right? You should always have in the back of your minds that everything you're building, it just winds up as rectangles at the end, which is really cool, but also kind of scary, right? If I asked you to go build a RISC-V processor, here's a bunch of rectangles, you'd look at me like I had 3 heads, right? That's an absurd thing to try. And the reason it works is because we have all these levels of abstraction, right? We can hide the rectangles behind transistors. We can hide the transistors behind standard cells and so forth. And then, of course, these rectangles are just, ultimately like some data file on your computer, and we need to send that off to TSMC or whomever to actually fabricate it into silicon hardware. And so even the rectangles are themselves an abstraction, because we don't need to worry about materials, fabrication processes, doping levels, all this stuff that you need to actually think about to build the thing. And so it's an even more absurd statement to say, here's a bunch of sand and chemical. Silicon's just sand, right? Here's a bunch of sand and chemicals. Please go build me a RISC-V processor, right? This is like a ridiculous thing to say, but that's effectively what you are learning to do in this class. And the way you are learning to do it is by managing complexity through abstraction. So we're going to dive into content in a moment, but every new thing that we're learning, every new lecture topic, it's helpful to just have in your back of your minds, like, what is the level of abstraction that we're at now? And then like occasionally we'll think about, oh, well, what happens if you go down a level? What does that look like, right? Or what happens if you go down another level? What does that look like? I think that's mainly what I wanted to say about abstraction. It's extremely powerful, but also kind of scary. One abstraction that we live with every day is that the ground beneath our feet is solid and doesn't move. That's a really useful abstraction most of the time. That we don't have to think about the facts that we're actually floating on these giant fragments of rock floating around on magma under the earth, until there's an earthquake and the abstraction breaks. And then you have to think about it a lot for a little while, right? So it's something that most of the time we can just abstract away and not think about it. But occasionally it's really important to know what's going on beneath. Any questions about abstraction or any of the other high-level concepts that we talked about just now before we start RISC-V stuff? Okay, I will get off my soapbox now. Let's talk about RISC-V. Many of you, if you've taken 61C, much of this will probably be familiar to you. If you took it a while ago, it might be useful to have a refresher. Today, we're going to talk about RISC-V at a high level, and then start talking about how we might design a processor from a hardware perspective. Obviously, this is very relevant to your final project in this course, and so we are going to spend some time on it, even though some of it will be reviewed from your previous course for those that have taken 61C. So many of you may be familiar with the RISC-V ISA and its history. It came, of course, from University of California, Berkeley, about 15 years ago. It's open ISA, so anyone can use it, which is really nice for teaching, but it also gets used in industry and in the wider world. It can run any kind of software that you might like. There are many different variants of RISC-V defined, different standardized variants, so that, again, you can build chips that target a specific architecture, the RV32 architecture, the RV64 architecture, and the software will know that any such chip implements that specification, and you can run on that. The base ISA is very simple. That's what we're going to be focused on for the next few lectures, called RV32I. It only has about 40 instructions, and so it's digestible and it's feasible to actually walk through how you would build a simple processor to implement it in a few lectures. There are extensions that do all of the important things that you might want to have. Multiplication, division, floating point math, many other things. The effort is, of course, outside of Berkeley now. It is transcended into the wider world. There's governance through the RISC-V Foundation. As a personal anecdote, so I started at Berkeley in 2012 in my PhD, right as RISC-V was sort of getting off the ground. I believe I would have to discuss with some other people to confirm or substantiate this claim, but I believe I was the first person to execute a RISC-V instruction on a chip back in late fall of 2012. We taped out, or the people in the lab before me had taped out this chip, and as a first-year grad student, I got assigned to testing it. The chip really didn't work hardly at all. It was very deeply broken. But through some heroic efforts, we managed to get it to run 2 instructions in a loop. So I think it would do an add and then just jump back to the previous instruction or something like that. But yeah, so not a successful research effort by any means, but I guess it has this little place in history now. So this is another view of abstraction, right? That was presented earlier in the course. This is more focused on how we design rather than what we design. The RISC-V specification is lowered into a model, often in C or C++, although in the Berkeley courseware and in 152, we use Chisel as the model. And then from that, we define the microarchitecture and design the logic for it in RTL, in Verilog. And so in this course, we will provide you the kind of upper parts of this. We'll provide tests as part of the class project. So we will specify in software what your hardware is expected to do to verify against this existing test suite. And over the next few lectures, we're going to talk first about a single cycle processor and then a pipelined in order processor, expanding on what you've already seen in 61C. Okay, so here's our very simple 1 instruction per cycle RISC-V machine. On every tick of the clock, the computer executes 1 instruction, right? We have all this state that's listed here. There's the PC, the program counter, there's the instruction memory, register file, the data memory. And then the current state is used to drive combinational logic, whose output settles at the next value and then is used to determine the next state. So at the rising edge of the clock, all the state elements are updated with the combinational logic outputs, and we move to the next cycle. This should sound very familiar from the last lecture and a half, right? This is exactly a finite state machine, right? We're exactly at the register transfer level of abstraction. We have some state. We have some combinational logic that's used to calculate the next state. And then we update the state again. Cool. We know how to design FSMs. You know, we've learned that now. You all are expert FSM designers. So this should be pretty easy, right? So what exactly is all this state that's required? Well, each instruction is going to read and update, some subset of this state during execution. Well, we have these 32 registers. In RISC-V lands, they're called X0 through X31. So each of those in the RV32I architecture is 32 bits each. And so we need a register file that holds 32 registers with 32 bits per register. We can figure out which registers to use. Remember, by looking at the RS1 and RS2 fields in the instruction, we'll again, in a few minutes, we'll remind ourselves about the instruction format and where we find those. How many bits are RS1 and RS2, by the way, each? Yeah, so these are 5-bit values. And why is that? Yes, in the back. Right, 2 to the 5th is 32. You need 5 bits to encode a 32-bit lookup, right? So each of these is 5 bits. Sometimes we'll have a write register or a destination specified by the RD field in the same way. X0 is always 0. That's just something baked into the specification. It's handy to have 0 around to read from. So that's the register file. Do folks know when a lecturer says recall, by the way? Or folks know what that means? When I say recall, it means you're supposed to have already learned this. I know you've probably forgotten, but let's just pretend that I'm reminding you. Okay, so recall that the program counter PC holds the address of the current instruction. That's pretty straightforward. It's just an address in the instruction memory. And then we have this concept of mem. In our cartoons and the subsequent slides, we'll break up instruction and data memory into 2 separate constructs. In reality, it's going to be one unified memory space. Also in our cartoon, these will be actual memories where you read instructions from them and then get that instruction out. For more advanced processor designs, these would be replaced with caches rather than the full memory themselves. for reasons that will become very clear if you spend more time in computer architecture land. We're not going to talk more about caches right now. We're just going to assume that this is a very simple processor with very small actual memories that don't have any backing store behind them. So that's the state that we need. And so let's go ahead and try to implement this FSM. Okay, well, we just saw how to code an FSM in Verilog, right? We need to have these parameter statements where we write out all our different named states, and then we just need to have some logic to jump between them. So how much state do we actually have here in our processor FSM? How many different states are there? As an aside, you're gonna get to know your neighbors a little bit today if you haven't already. So why don't you turn to your neighbor and introduce yourself if you haven't met yet, and then discuss this question: how many different states, how many different circles do we need to draw in our state transition diagram to implement this finite state machine? Okay, let's come back together. Let's bring our attention back up here, please. Were any pairs able to figure out and want to hazard a guess for the crowd? How many actual states do we have in our FSM, our RISC-V FSM here? Yes.
Memory as part of the system that we're like saying.
Is that a architectural state in RISC-V?
I don't know.
Well, let's think about it. One way of thinking about architectural state is if I save all of the architectural state and then power down the computer and delete it all, and heck, you can throw out that computer and get a new computer that implements the same specification and load that architectural state into the new computer and turn it on. It will keep executing the program just the same as if you hadn't done anything, and it'll still get the same answer. So based on that definition, is the data memory architectural state? Who thinks it is? Thumbs up. Who thinks it's not? Thumbs down. Okay. Why do you think it is? Yes.
I guess your instructions are saved in like memory space, so we're transitioning like states.
Yeah. So, and what's your name? Okay. So Peter's saying, well, your instructions are sitting in memory, and if you throw those out, the program will not work anymore. So certainly, instruction memory is definitely state that we need to keep around. That sounds reasonable to me. What about the data memory? Yes.
You're gonna bench, like if we were in the original computer, we were gonna bench the thing up and then execute using that.
Okay, and your name is Chuyan. Okay, so Chuyan's comment is, well, you know, if you're shutting off this computer, and to give a concrete example, let's say the very next instruction you want to execute is a load word, right? You're gonna go look in data memory, for the very next instruction. So when you power on that new computer and load in all the architectural state, that word in data memory better be sitting there so you can grab the right one and get the right answer. So registers are architectural state. The program counter, clearly, both instruction and data memories are architectural state. It seems like kind of a lot, right? So back to the original question, how much architectural state, how many different states are there in our FSM? Yeah. Yeah, go ahead. Yes, in the red shirt. 4. So there's 4 different sources of state. But like, let's imagine we're trying to draw our straight state transition diagram, right? Where this first bubble is you've just come out of reset, everything is 0. You've loaded in the program memory. That's it. That's our first bubble. How many different bubbles are there in our state transition diagram? Right. So every bit of state can be 1 or 0. So that's a lot. It's two to the very large number. Two to the sum of the number of bits in your state. I'm quite certain that that's more than the number of atoms in the universe. So maybe this abstraction or this way of thinking about how to design a RISC-V processor as a big state machine is not the most useful way of designing it. To be a little more explicit, let me clear the annotation here. If you would just try to design it the same way that we were thinking about general FSMs, we had our cat FSM with 3 states or whatever. That was pretty manageable in Verilog. It doesn't make sense to list out billions of states and their transitions in our Verilog block, right? For a number of reasons, that's not feasible. It's hard to reason about. It would be effectively impossible to implement a blob of combinational logic that is just defining every transition from one state to the next. So we're going to come at processor design a little bit differently. We will use finite state machines as a subcomponent of how we're thinking about our processors. But instead of just having one big blobby FSM, we're going to break things up into stages. We're going to distribute our architectural state between the different stages. And then we're going to think about how data is flowing from one stage to the next, how those are controlled from kind of a central controller, in order to come up with a more useful design abstraction for building our RISC-V CPUs. And in particular, well, let's call this processor implementation a data path, just for simplicity, although there's other things going on besides manipulating data. That's fine. When we have these 5 stages of a data path, right? Which maybe this is ringing a bell from your 61C days. So stage 1, instruction fetch. We're going to figure out which instruction we're reading out of the program counter. IF. Processor designers love acronyms. So in a few slides, we're going to be all acronyms here. Hopefully that's not too bewildering, but you will get used to it one way or the other. Stage 2, instruction decode. So this is saying, okay, we have this instruction. Let's look inside it and figure out what we're supposed to be doing. Stage 3, execute, actually do the thing that the instruction says. Stage 4, memory access. So perhaps the instruction, not all of them do, but perhaps the instruction asks us to read or write from a memory. Let's do that. And then finally, stage 5, write back. Again, not every instruction does this, but many instructions will write something back into the register file after reading out of it. And so that happens in stage 5. Okay, so these are the 5 stages of the data path. Now let's think about, from a hardware perspective, at a high level. So we're sort of at the microarchitecture level of abstraction here. How would we actually take our state elements, place them into each of these stages, and wire them together? Okay, so we'll start with the program counter. In instruction fetch. The program counter is going to send an address to the instruction memory, which will then read out the data, which is what instruction we need, right? So that's all that instruction fetch is doing at a high level. How do we decide what the program counter should be? We'll come back to that. And this by the way is a register. We'll put that little triangle up there to indicate that something is happening on the clock edge there. It has some state, some register state. We're then going to decode this 32-bit bus into, make this longer, RS1, RS2, RD, and these are how many bits again? Shout it out. Yeah, that's right. So we're just picking out 5-bit slices that are the key slices out of here. And then these are going to be addresses, 5-bit addresses into the register file, which is a clocked element. Okay, and so we've done decode. We also throw register read into the decode stage. Okay, so out of the register file comes some data. And then we probably want to do something with that data. Like say an add or a subtract, you know. And so this is our ALU. I made it too small, so I'm going to label it down here. The ALU is just doing whatever arithmetic you might like. And that's execute. Okay, we get the results of that execution. Perhaps the instruction tells us to write that into our data memory. Which is also a clocked element. Or perhaps we didn't need to do any math. We just needed to send this data directly into the data memory. That's okay. And actually, I'm going to, it'd probably be more accurate to draw this as a mux, right? All right, because we're selecting either the output of the ALU or just the direct output from the register file. There are more details that I'm eliding here, right? But this is kind of at the high level what's going on. So we'll write that into the data memory, or maybe we'll read something out of the data memory, or maybe not. But in any case, we might want to write it back to the register file in stage 5. And then we'll add one more level of detail or information here, which is, well, where's that next instruction actually coming from, right? And so in most cases, we're just taking the previous program counter and adding 4 to it. And then that's our next instruction to execute. That's our next value of the program counter. Why are we adding 4, by the way? Could someone remind us? Yes. Okay. And so how do we get 4 out of that? Sure. Yeah. So everything's byte addressed, recall. So we need to step 4 bytes in next in the memory to get the next instruction. And your name?
Nicholas.
Nicholas. Okay. Thank you, Nicholas. The other case where we don't just want to advance by 4 is, this is going to get a little clunky, so pardon this, but so we might have actually calculated a new address to jump to in a branch, right? So the ALU may have been actually calculating on addresses instead of data. And then we've calculated a new value for the program counter, which is the branch. So this is our kind of high-level microarchitecture diagram of a simple single-cycle RISC-V processor. Again, this I'm hoping for many of you is review from CS61C because it's similar to what we presented there. Any questions about what I've drawn so far? All right. So now let's think about this as hardware designers, right? This seems a little perhaps intimidating to implement, right? It's not just a simple combinational logic block. It's not a finite state machine. It's something else. It's something with more going on. But here are some nice things. One nice thing is that it has these 5 well-defined stages with specific things going on in each stage, specific inputs and outputs to each stage. Another nice thing is that it's actually made up of these simple components, right? If we look at each of these components in turn, they're not that complicated. And so let's go ahead and do that next. Let's look at each of the components in this diagram in turn, and think about how we would implement them in hardware, generally, or perhaps in Verilog specifically. So clear that so we can look at the next page. Here are some combinational elements that we saw on the previous slide. We might have an adder, right? For example, to calculate PC plus 4. That's a special adder where it's always adding 4. Usually you have an adder that's adding 2 arbitrary things. But we know how to implement an adder in Verilog, right? You can just do something like aside sum equals A plus B. There's a few things I'm kind of hand waving away right, when I've written this, right? Like where's our carry out in this A plus B statement, for example? Something to think about. We're not going to go into it right now. Another key concept is a multiplexer. You all have probably come across these in your lab work already. If not, you will soon. One straightforward and elegant way to implement a multiplexer is to use this tri-state notation. So we can say select question mark A colon B. Have folks seen this notation before? It's similar to C notation as well to do a similar thing. So this is saying if select is 1, then the output is A, otherwise it's B. Okay. So that's a nice one-liner to implement a mux in Verilog. An ALU, as I mentioned, is not just doing adds, it's doing other things, but that's not too scary. It might be nice to implement this ALU as a always combinational block. So we do always add star, right, for combinational logic. And then we could have a case statement. And perhaps if our opcode is 0, then we'll say R equals A plus B. If our opcode is 1, then we'll say R equals A minus B. If our opcode is 2, we'll say R equals, I don't know, what else should we implement? How about a left shift? I guess I'm being inconsistent in my capitalization here. I apologize. And you can add as many items to this case statement as you like. So that's not too bad. We have a nice little programmable ALU where we can select which function we want to do. So these are some combinational components of the data path. Not too bad so far. And yeah, I'm trying to figure out a way to give these lectures where I don't have to clear the annotations to move to the next slide, by the way. But I haven't quite figured out a good way to do that yet. So I apologize for writing everything and then deleting it. I will try to fix that in future. Let's move on to the state elements in our RISC-V data path. So this is just a register. The program counter, for example, was a register, was a potentially 32-bit register if you have a large instruction memory. It's slightly different than the registers we looked at just because it has a write enable, right? So it has a signal that's saying yes, do the update, or no, don't do the update, a combinational signal. But that's not too scary. We could just do something like always at pause edge clock. If write enable, out gets in. So that's a straightforward way to code this up in Verilog. Again, I'm enlightening some complexity. What's one important thing that I haven't written here, but you would actually absolutely need to write down if you were implementing this for one of your labs? Yes. Begin end is important, but not actually necessary for this case, because I only have a single statement. Right. So you're absolutely right. You could insert a begin and an end statement. But what I've written is syntactically correct. Although it's a good habit to always use begin end. Yes. So you could write an else statement that said otherwise out keeps out, but that's actually redundant because registers keep their state kind of by default. So we're saying, if write enable do this update, otherwise don't do anything, in which case it'll just remember the previous state. Yes. Yes, you're right that I've elided some of the boilerplate naming the variables and so forth. There's one other important thing that I'm thinking of. One other signal that is going to be in play for any state register that you want to implement. Yes, we need a reset. We need to be able to reset these registers so that they come into the world when you power on the chip in a known state. Otherwise, it's not going to be pretty. It's not going to be pretty in simulation, and it's not going to be pretty in silicon. So I'm not going to write out the reset code here, but it is definitely something you would need to think about for all of these state elements, what reset looks like. Yes, question.
How did it differ from when we have to make sure to not make latches? Is that a different?
Yeah, so the key here is that we're in a sort of register style block where we have this always at pause edge clock statement. You can think of always at pause edge clock as a keyword that the synthesis tools are going to look for and identify and then synthesize safely a register. If this were instead always at star, and I didn't define all of my cases, then you would get a latch, because then it's saying, well, it looks like you may have wanted to implement combinational logic, but I need to keep some state around, and so I'm going to just stick a latch in there. Yeah, this is a little bit of a subtle point. So I do want to move on, but we can chat about it more after lecture and office hours. Okay. Let's move on. I better clear this drawing here. Data path elements part 2. Well, we have this register file, as we talked about. It seems to have, I guess, three different addresses that can be input, as we talked about, right? It has RS1, RS2, and RD. Here they're denoted as RA, RB, and RW as the inputs to this block. And then it has one input bus, a bus W, which is the 32-bit bus that we use to write data into this thing, and 2 output buses. It also has a clock, not shown here as a reset signal, very important. And so we select which registers we want to use. We read them out, and then we do the write. It's clocked in this example. We're actually clocking it only during the write operation. So we can kind of read things out when we like, but we're only going to update the state when there's a write. So this was much more complicated than the simple register that we had on the previous slide, right? There's 3 different address outputs. There's different buses floating around, but the implementation is not actually too scary. It's shown here. So we list all our inputs and outputs. Again, aligning reset for simplicity, although this is something you would have to think about in a real implementation. Note this syntax for a 2D register array. This is how you would write that in Verilog. So this is saying, you know, a register of 32 registers, but then each of those registers itself has 32 bits, right? So that's how we get all the state. And then on the clock, on the pause edge of the clock, we update the write if write enable is asserted. And then we just read out the reads combinationally. And you note, again, we have this tri-state syntax because if we're ever reading from X0, it's always 0. We don't actually even need a register to do that. And so I guess you could actually save a register, right? Because you don't need to have a register sitting there storing zeros. But it's shown this way for cleanliness. How does this is all for RV32I, right? Which is the architecture that we're targeting. RV64I would be a little bit of a different beast, right? Because it's manipulating 64-bit data instead of 32-bit data. So what would the RV64I register file look like? And let me ask that question a little bit more concretely so you can discuss it. I've numbered the lines of Verilog here. So turn to your neighbor and figure out which lines of Verilog would need to change to implement the RV64I register file. Still has 32 registers. Yeah, they're of a different size. So let's think about how much data we actually have, right? We have 32 entries in the register file. Yeah. Each of those is 32 bits. Yeah. Right. So for the reg statement, you get to write down how many bits you want. Oh, 32. Okay. Let's come back together. Who can suggest some lines that need to change? Just tell me the line numbers in the interest of time. So yeah, someone said 5 through 7, right? Because these buses should all be of width 64 now. 9, yeah, but which part of 9, right? So specifically, we still have 32 registers, but now they are of width 64. That's the confusing part about this example, right? Anywhere else that needs to change? Yes. Lines 2 through 4.
Never mind, right? There's only still 30.
There are still only 32 registers. Yes, I was going to ask someone to see whether they agree, but you actually solved it yourself. Yeah. So the number of registers has not changed. The addresses don't need to change. Yeah. Oh, yeah. This is a subtle one, but you do really want to make sure that you're assigning 64 bits of 0 in the case of X0, right? Anything else? This last one's kind of a gimme, but you should probably rename the module, right? So RV64I reg instead. Okay, we only have a few minutes left, so I'm going to move on and I'll have to take questions after lecture because I do want to wrap this up. Finally, let's talk about our data path elements, which are the memories, right? We're going to talk later in the class about exactly how you build a real memory. It's always an option to just build the memory as a sea of registers, as we saw in the previous slide. But for larger memories, this quickly becomes impractical from an implementation perspective. Again, we need to break the level of abstraction and look down one level to understand why you might just not want millions of registers floating around in your design. It would work. It would give poor performance, power, and area are key metrics for processor design. And so in practice, we're going to build memories a different way, but we'll talk about that later. For right now, we'll bury that all under the rug. Just treat this as a magic memory. It's got one data in, one data out. It's got a write enable. It has an address. And it's clocked the same as the previous slide. So the details of how, so you could write this down in Verilog the same way as we wrote down the register file in Verilog on the previous slide. In practice, when you go to build this in your ASIC and FPGA labs, these memories will look different, and they will look different depending on which lab you're in. And so we'll defer the details of how to implement it to those labs. We'll defer the details of what you're actually implementing on the FPGA and ASIC to a future lecture when we're breaking that layer of abstraction. So I hope now when we look back at our RISC-V data path from building blocks, you should look at every construct, every block on the slide and think, oh, that's a simple building block. I basically know how to build that, right? And so now we can be comfortable kind of breaking the microarchitecture abstraction, going down one level to the register transfer abstraction, and still know, yeah, I'm not afraid of that. I basically understand how to build all those pieces, or I have some rough idea. So in summary, the RISC-V processor, conceptually, it's a large state machine. Practically, we implement it as this data path and control. Next time, we're going to start actually working through how to build this thing, okay? This is very cool. I found this lecture very cool. I still remember it back all those years ago in undergrad. But I do want to get a sense as we close here, some of this or much of this will be review from 61C. So if I throw this diagram up on the slide with all of its apparent complexity, can folks just give me a fist of 5? Where 5 is, yeah, I remember every single bit of this from 61C. I could draw this from memory. And 0 is like, I'm totally bewildered and have no idea what's going on here. Okay, thanks. It looks like the median is about a 3. There are some zeros, which is fine. I know not everyone has taken 61C, which is fine. Particularly grad students, if you did your undergrad elsewhere. So we will go through all this and make sure everyone is comfortable with how to design this thing in the next 2 lectures. Thanks, everyone.
So RP32I.
Yeah.
Why is it 32D0 instead of 32D0?
Yes. Oh, sorry. The D just refers to how the number afterwards is represented. And so this could actually be 32B0 or D0 would both be valid. This is just saying that this 0 is a decimal representation. It would be legal to say 32 tick D5. It would not be legal to say 32 tick E5, right?
Oh, I see.
Yes, of course. Okay.
I really have no is there any quickly get me started? I can get
Yeah, so I would recommend getting the Harris textbook. That's kind of the Bible for this class, at least from my perspective. That's what I believe the 61D lectures from previous semesters, possibly even the current semester, should be available on the EECS website. You might ask Prof. Chow, actually, she would have more knowledge about that. But yeah, I would say 61C would be useful background material to kind of get a start. Yeah. Yes, if your background is all analog stuff, then you know things that a lot of folks in the class don't know, but then some of it might be a little bewildering. Okay, good luck.
I'm a little confused why this stays like 40 and not 50.
Okay, yeah, good question. So the RV64I spec is not changing the number of rows, the number of registers. It's just changing their width.
Okay, that makes sense.
So there's still 32 of them, and so we still only need 5 bits to pick which of the 32 they
Right.
are. But then each one has 64 bits of data instead of 32.
And RW stands for read write.
No, in this syntax, A and B are the input, or I'm sorry, A, B, and W are all inputs, but W is a write address, whereas A and B are the read addresses. So the R is for register. I actually don't love this syntax choice, but yeah, in this slide, R is for register. So this RW would be register write, the address to write, and then RA would be read the A.
Like access.
It's just A and B as 2 inputs, as 2 generic input names. So I would.
So if you want to do like addition of 2 numbers, you would like look into the register file for the 2.
Exactly. You pick the 2 numbers out of the register